Hello, this is the second part of our mass spectrometry lessons. In the first video lesson, we talked about mass spectrometers in general, and we talked about ionization sources. And in this video, we are going to talk about mass analysis. If you haven't watched the first video, I strongly recommend you to watch the first video so understanding this video can be easier for you. Okay, here we go. Um, Mass analysis are the second vital, let's say, instrument of mass spectrometers, and different types of mass analysis have been used for different types of mass spectrometers. And today we are, in this video lesson, we are going to talk about them. We are going to understand how they work. And they are classified as magnetic sector, quadrupole, time of flight one, ion trap one, orbit traps, and Fourier transform, ion cyclotron resonance mass analysis. And they have their own mechanisms, advantages, limitations. So I hope this lesson will be interesting to you. Okay, the first one, magnetic sector. Magnetic sector uses magnetic and or electric fields to separate ions by mass over charge, and they are of very high resolution, but bulky and expensive. Here we can see how different ions can be separated in a magnetic field. The low mass to charge ion B is separated from high mass to charge ion A as they pass through the magnetic field. Since the ions are charged as they move through the magnetic sector, as indicated here, the magnetic field bends the ion beam in an arc. The first mass spectrometer built by J.J. Thomson used a magnet, as indicated here, to measure the mass over charge value of an electron. Magnetic sector instruments have evolved from the same concept. Sector instruments have higher resolution and greater mass range than quadrupole instruments, but they require larger vacuum pumps and often scan more slowly. So by the mass range, we say that magnetic sector can be kind of advantages compared to quadrupole, but it requires larger vacuum pumps. And by this, okay, we say it can be a kind of problematic. It might cause some extra issues. And on the other hand, it scans more slowly. The typical mass range is up to around, let's say, to around 5,000 mass to charge, but this may be extended to 30,000 mass to charge ratio. Magnetic sector instruments are often used in series with an electric sector described below for high resolution and tandem mass spectrometry experiments. Magnetic sector instruments separate ions in a magnetic field according to the momentum and charge of the ions. Since different molecules have different molecular weight and charge, so we can expect this kind of separation in a magnetic field, resulting from the ion momentum and ion charge. Ions are accelerated from the source region into the magnetic sector by a 1 to 10 kilovolt electric field, and this acceleration is significantly greater than 100 volt acceleration typical for a quadrupole instrument. So compared to quadrupole instrument, the voltage of the magnetic sector is 10 to 100 times greater. Okay. And this is the quadrupole, the second type of mass analysis. It has this kind of, let's say, instrument consisted of 4 different types of rods. 2 of them are negatively charged, 2 of them are positively charged. Quadrupole uses oscillating electric field, filters ions and specific mass over charge ratios. And it is common, robust, and relatively inexpensive compared to some of them like magnetic field, I would say. Okay. compared to Fourier transform cyclotron ones at least. Okay, quadrupoles or quads, this force play a crucial role in mass spectrometry. These four cylindrical rods powered by direct current and radio frequency voltages significantly enhance analytical sensitivity and selectivity in DC current. Okay, DC current can exist in batteries. For information, let me remind you, and AC is and electricity in our homes. Yeah, it uses DC and radio frequency. And significant these parameters, these factors significantly enhance analytical sensitivity and selectivity of the quadrupole. In a quadrupole mass spectrometer, the rods create an electric field. As we see here, electric field exists among the charged electrons. That electric field allows only ions with a specific mass to charge ratio to pass through. And by adjusting the radio frequency and DC voltages, users can selectively transmit target ions, making quadrupoles highly effective for isolating analytes. Beyond mass filtering, quadrupoles improve ion transmission by capturing and transferring ions with minimal loss. They also function as collision cells, breaking down ions into smaller fragments for detailed analysis. And how they can be used in different modes, because different modes can be selected for a single, let's say, quadrupole. These capabilities make quadrupoles essential in modern mass spectrometry. They operate as mass analyzers, transmission elements, and collision cells, offering unmatched sensitivity and adaptability. This guide compares single and triple quadruple mass spectrometers and explains when each is most effective. We are going to see some more information about quadruple here. There are two types of quadruples, at least single quadrupole and triple quadrupole. A single quadrupole mass spectrometer uses one quadrupole, as indicated here. In triple, we can see consecutive three quadrupoles of this one. And a single quadrupole mass spectrometer uses one quadrupole as a mass filter or scanner, allowing for basic mass analysis. And triple quadrupole mass spectrometer contains three consecutive quadrupoles, significantly enhancing performance. The first quadrupole is responsible for selection of ions of interest, and the second one acts as a collision cell to fragment ions, and the third one filters and detects product ions for precise identification. So by the function, we see that triple quadrupole mass spectrometer is considered advantages over the single quadrupole mass spectrometer. Single quadrupole mass spectrometer supports both qualitative and quantitative analysis. In scan mode, as I highlighted earlier, in scan mode, it systematically transmits ions through the quadrupole, generating a full scan spectrum for qualitative analysis. In selected ion monitoring mode, it isolates and measures specific mass over charge ions, improving sensitivity for quantitative applications. So at least in two different modes, single quadrupole mass spectrometer can work, can be used. And triple quadrupole mass spectrometer, however, excels in multiple reaction monitoring mode. Because it has three quadrupoles. By tracking specific precursor to product ion transition, multiple reaction monitoring dramatically increases sensitivity and specificity, making triple quadrupole mass spectrometer ideal for detecting low abundance analytes in complex samples. Okay, here we compare two types of quadrupoles, the SC ion 8700 single quadrupole, and the SC ion 8900 triple quadrupole. The single quadrupole by this model mass is a state-of-art detector. The single quadrupole is designed to enhance the capabilities of our gas chromatography system. It is ideal for today's fast-paced analytical laboratories. This single quadrupole mass spectrometer detector features a lens-free ion path, heated on optics, and an extended dynamic range detector. The single quadrupole mass spectrometer enables precise quantification. This one enables precise quantification and identification, making it a multi-purpose instrument for target and on-target analysis. And this one is advantages in a way. In contrast, the 8900 triple quadrupole mass spectrometer excels in achieving low detection limits, especially in complex matrices. So low abundant compounds can be analyzed by triple quadrupole mass spectrometers. Operating in multiple reaction monitoring mode, the triple quadrupole mass spectrometer isolates and monitors specific fragment ions of target compounds, and it effectively reduces chemical noise and enables highly accurate quantification. So by these properties, triple quadrupole mass spectrometers have advantages over single quadrupoles. The impressive speed of the multiple reaction monitoring allows the analysis of hundreds of compounds in a single run without sacrificing quantitative performances. So the advantages of the triple quadrupole is not only in the detection of low abundant compounds, but also hundreds of compounds in a single run can be carried out. The identification of hundreds of compounds can be done in a single run without sacrificing quantitative performances. Okay, next. The third type of mass analysis is time of flight. Um, it separates ions based on flight time of flight. So based on the flight time, this kind of mass analyzer enables the separation of ions, and it lighter ions. Lighter ions here travel faster, and high speed and wide mass range can be provided, can be detected and used for the separation of ions. The MALDI, matrix assisted laser detection, laser desorption ionization method is coupled with a mass analyzer as MALDI-TOF. Uh, MALDI-TOF is the tandem of a MALDI ionization method and time of flight mass analyzer. So in TOF, the time ions take to reach the detector is measured. The velocity is determined by the mass to charge ratio. The smaller ions will reach the detector before the large ones due to the fact that they have less mass, since the potential of the smaller ions is less, so their flight is faster. The charge of the ions also determines the velocity as well. Ions with two or more positive charges will move faster than ions with only one positive charge. Let's say a charged molecule with a mass 154 plus 3 can reach the detector faster than the molecule with a mass 154, but the charge is lower, let's say plus 1. Thus, those ions that are both smaller and positively charged will move faster. However, we have to keep in mind that non-charged fragments like radicals won't be detected by time of flight. By TOF, we can identify only charged mass over charge particles. The output of the detector is the mass spectrum and displayed in a stick diagram. This shows the relative current produced by ions varying mass charge ratios. Here we can see by using MAUDI here on the plate, as we talked in our first lecture on mass spectrometry. Here on the plate, the mixture of the matrix and the analyte is installed by using the laser. They are uh, subjected to the volatile state. So by the flight of time, they can reach the detector and identify. So, and here reflection can also be observed. The reflected from the detector and compounds, I mean ions, can be identified in another detector after reflection as well. So this is how the TOF can work. The fourth type of the mass analyzer is ion trap. Here we can see how the ion trap can work. It traps ions in electric fields and ejects them sequentially. We can consider this is a part of the quadrupole, or it can be considered as a separate, let's say, method or mass analyzer. The scheme of a quadrupole ion trap of classical setup with a particle of positive charge, dark red here is indicated, and it is surrounded by a cloud of similarly charged particles in brown color. Yeah, and the electric field E. Here is E and here is E. Yeah, is generated by a quadruple of end caps A positive, and here B positive, A is minus, and ring electrodes. And in picture 1 and 2, here we can see differences in the orientations of the charged particles. So this is the, let's say, one of the factors that can explain the essence of ion trap. This analyzer employs similar principles as the quadruple analyzer mentioned above. It uses an electric field for the separation of the ions by mass to charge ratios. And after entry, the electric field in the cavity due to the electrodes causes the ions of certain mass overcharge, mass charge values to orbit in the space. As indicated here, as the radio frequency voltage increases, heavier mass ion orbits become more stabilized and the light mass ions become less stabilized, and they cause them to collide with the wall and eliminate the possibility of traveling to and being detected by the detector. Okay, next one is orbit traps. Orbit traps have high resolution, very high resolution and accuracy. It measures ion oscillation frequency, and ion oscillation frequency is the, let's say, main power to generate, I mean, to explain its mechanism of action. The orbit trap is an ion trap mass analyzer that consists of two outer electrons in the quadruple ion trap. We said there are four electrodes, two negatively charged, which are located in front of each other, and two others are positively charged. So this is the let's say, power to trap the ions there. And in the orbit wrap, as we see here, it has two outer electrodes and one central electrode, as indicated here. And these three electrodes enable it to act as both an analyzer and detector. So this instrument plays the roles of analyzer and the detector. Ions entering there, the orbit wrap are captured through the electrodynamic squeeze. And after electrodynamic squeezing, they oscillate around the central electrode and between the two outer electrodes. Here we can see they form the oscillation around the central electrode. Different ions oscillate at different frequencies, resulting in their separation. By measuring the oscillation frequencies induced by ions on the outer electrode, the mass spectra of the ions are equipped using image current detection. Orbitrap mass spectrometers deliver a total possible maximum resolution of 1 million at 200 mass to charge and sub minus part per million mass accuracy in a single compact and easy to use instrument. These high resolution accurate mass systems detect a wide range of compounds and small molecules during both targeted and untargeted analysis without losing selectivity and sensitivity. Let's say by the accuracy, Orbitrap is highly, let's say, accurate and provides high resolution, and it can be used for high molecular compounds and for lower molecular compounds, both for targeted and untargeted cases. And without losing, it can select without losing the selectivity and sensitivity, it can be effectively used. Simply put, when it comes to orbit wrap technology, there is no compromise. Okay, highly accurate and can be used for a wide mass range. And the sixth type of the mass analyzer is Fourier transform ion cyclotron resonance. In this technique, the mass to charge ratio of an ion can be experimentally determined by measuring the frequency at which the ion is processed in a magnetic field. It has this kind of, let's say, outer vision. It is very expensive and ultra high resolution is provided by using this kind of mass analyzer. It uses magnetic field plus and cyclotron motions. And these frequencies obtained there, which are typically in the 100 kilohertz to megahertz region, can be very accurately measured with the modern electronics. And the detection scheme in the ICR, ion cyclotron resonance mass spectrometers, does not require destruction of the ions and allows us to do MSN ion molecule reaction and isotope exchange reactions. An infrared laser beam can also be introduced in the ICR cell and intersected with the ion pack to record infrared spectra through photofragmentation. We talked to you about Fourier transform infrared method. I recommend you to watch that video in order to understand the essence of this tool. So this is the regular type of mass analyzer. Again, it is very expensive, but it provides ultra high resolution. So this is, let's say, a quite expensive tool. I think in Uzbekistan, we don't have this kind of ultra high resolution providing cyclotron resonance. Okay, now we talked to you about six different types of mass analysis as indicated here: magnetic sector, quadrupole, time of flight, ion trap, orbit trap, and Fourier transform ion cyclotron resonance. And now we are going to summarize this data. Mass spectrometers can be classified by instrument configuration as single analyzer or tandem, let's say, mass spectrometry. And the single analyzers can include one mass analyzer like quadrupole, and in tandem we can see MS-MS, and two or more analyzers. The example can be a triple quadrupole. So by the instrument configuration, they can be single analyzer or tandem analyzer. And by the combination with other, let's say, separation methods, the MS can be classified as GCMS or LCMS. In GCMS, gas chromatography mass spectrometers, we can use electron ionization or chemical ionization. In liquid chromatography mass spectrometers, in which mass spectrometers are combined with HPLC, we can use electrospray ionization and MALDI, matrix-assisted laser desorption ionization method. And they can be also classified as quadrupole, TOF, orbitrap, etc., according to mass analysis. And according to ionization methods, they can be classified as electrospray ionization, MALDI, electron ionization, and according to instrument design, it can be single or tandem, as we talked, and they can be also hyphenated as GCMS or LCMS. These are all for this video lesson. Again, I ask you to support us with your likes if you like these videos, so that the video lessons can reach the wider audience. And I express my thanks for your time. Have a good day.